Welcome back to week 5. This week we will continue discussing about consumers. We will wrap up our discussion on consumers, and if possible we will move to talking about a market environment. So we learned there are 4 building blocks on consumer side. 3 we have already discussed. First was consumption set. We denoted it by capital X, and we can say that if there are n goods, and we can conceive all different permutation and combination of these n different goods. So then we can say that in this case X is equal to the positive orthant of n dimensional real space, where all goods are non-negative. For example, x1 to xn such that xi is greater than or equal to 0 for all I. That is what we have discussed. Then we move to feasible set, and we talked about largely budget set, and then we said not all these consumption are feasible for a particular consumer given financial, legal or geographical constraint. So we talked about the budget set, and this one can say what is in your pocket. Money is in your pocket that you use to buy items in the market, and prices you don't determine, prices are mostly of the time is given to you. Then we move to something that we call preferences, your liking. That's hardwired in your mind, what you like more. Of course, a psychologist would talk about why you like coffee more than tea and get into the genesis of this preference, but in economics we will take your preference as given and we will deal with it. And we realized that if certain basic properties are satisfied, then your preference can be represented by a utility function, and we also said that utility function is not unique. If a utility function represent your preferences, likings, then any monotonic transformation of that utility function will also represent your liking. And in that sense, your preferences are ordinal in nature, that only order is given. A number, particular number being associated with a meaningful sense is a difficult idea to digest, that I like coffee 10 times more than tea or something like that. That's way more difficult to talk about. Now, fourth is a behavioral assumption, and that will sound very obvious, but nevertheless, because we are writing a model, we should be clear about it. The behavioral assumption is simple, that given the preference that you have, you would pick a bundle from feasible set that gives you maximum level of happiness, maximum level of satisfaction. That's a behavioral assumption, and it's a, we make assumptions which should be acceptable to almost everyone. That's not a difficult thing to accept, that given our preferences and feasible set, we pick the best bundle for ourselves. That's what this behavioral assumption is saying. Now let us move to the consumer problem. How can we represent the consumer problem? So if we denote all the bundles which are feasible by, let us say, B of X, B represents the budget, so we can say this is the budget set. What is the idea? The idea is to pick one X star in the budget set such that that X star is at least as good as any X in, let us say that this X is any element in the budget set. So you are picking the best element. That's what the consumer problem is. It's coming from your fourth building block, the behavioral assumption, and that's what we are writing. We can also say what is B of X. The way we have written, B of X is combination of all X such that X belongs to the consumption set, and Px, of course here I am using the vector notation, P multiplied by X. If it is n dimensional, it is going to be P1 x1 P2 x2 plus Pn xn. This has to be less than or equal to I. So, you have to do that. So, but here everything we are writing in terms of preferences, which could be difficult to deal with. So, we can use utility function representation, and it makes our life simpler, and that is maximize u of x. X is an argument. So, with by changing the argument, we have to figure out an argument, a bundle that maximizes your utility such that Px is less than or equal to I. So, it ensures what is happening, this constraint ensure that you find your x well within the budget set, and you are varying that x to get the maximized utility. So, this is the way one can represent the consumer's problem. And as this is in algebraic form, we can very easily, or this is in the mathematical formulation which does not depend on set and all. So, it is much easier to solve than the previous problem. So, let us write the simplest of the problem. We say that maximize utility, let us say in the 2-dimensional world, the argument can be extended to n-dimensional world. You have to how? By varying x such that P1 x1 plus P2 x2 is less than or equal to I. For time being, what we are going to do, that instead of saying less than or equal to, we will say equal to. So, now if we do what we say, here is x1, here is x2, and here is, let us say this is P1 x1 plus P2 x2 is equal to I line. We have to be on this line if we say that P1 x1 plus P2 x2 is equal to I. If we say less than or equal to, then all the bundle within would be permitted, that we had discussed. So, in a way we are revising also. And so, we can proceed how to do that. Let us say, and we have already done it once in the cost in when we talked about cost minimization. We are going to do it again because it is quite important that you understand this technique. We can say, let us say x1 star x2 star is that bundle which maximizes u of x1 comma x2. So, if it is maximizes, what we can say, P1 x1 star plus P2 x2 star has to be equal to I, because this constraint has to be satisfied. So, it has to be on this line somewhere. So, this is the line. Now, because it is equal to, we have the only freedom to move in this direction, or we have freedom to move in this direction. We have to be on that line. So, basically here I1 is being spent on good 1, I2 is being spent on good 2, and total is I. What we can do, we can take little bit of income that is being spent on good 1 and decrease I1 by this amount and give it to I2. And this has to be equal to I, because we have to be on that line. So, because of this change, because now we are having different amount of good 1 and good 2, so our total utility would change. So, let us say the rate of change in utility because of a change in x1 while keeping x2 fixed is mu1, which is del u del x1. How many units of less of good 1 can be bought, because now delta I less income is being spent on good 1, and that is going to be delta I divided by P1. So, this is less, that is why we will put a minus sign, and this is the rate. So, the total change is going to be mu1 multiplied by minus of delta I P1. This is the way we can write. And what is happening similarly, now delta I is going to good 2. So, this is going to be delta I by P2 more of good 2, and because of more of good 2, this would be the increase in utility. And if the original bundle was maximizing, this change cannot be greater than 0. If this change is greater than 0, then what it means, that the new bundle gives higher utility than the earlier bundle, and what it means that earlier bundle must not be maximizing your utility. So, if this is really maximizing your utility, this has to be true. And similarly, what you can do, you can move, you can have a different instance where you increase expenditure on, in the earlier case this should have been positive, then only it would be equal to I. Yeah, so in this case let us make it positive, and if this is positive, then let us make this negative. So, basically this will get cancelled, and in this case your same argument will give that this is, we can write it this way also. How did I write it? I took this here and this here. So, that you have to be mindful. So, let me write original way first. So, because now delta I more is being spent on good one. So, this is more of good one this person can buy, increase in utility would be this much, and decrease in utility because now less of good 2 is being bought is going to be this, and this both have to be equal to 0. So, if we use both the equation, they have to be satisfied simultaneously. So, here basically whole side of this inequality can be divided by delta I. So, it will get cancelled because here is 0, there would not be any change. So, we can write the first one is mu1 divided by p1 plus mu2 divided by p2 has to be less than or equal to 0. And from here we can get mu1 divided by p1 minus mu2 divided by p2 has to be less than or equal to 0. And these two have to be simultaneously satisfied. Notice that first one is the negative of the second one, or you can say the second one is the negative of first one. So, they can be satisfied at only one point when you have both of them as equal to 0. So, mu1 divided by p1 is equal to mu2 divided by p2. This is the argument we get. This can be rewritten as mu1 divided by mu2 is equal to p1 by p2, and then we can put minus sign on the both side. When you put minus sign, what is this equal to? This is marginal rate of substitution. This is the slope of the budget line, slope of the budget line, and this is the marginal rate of substitution. Exact same argument we had obtained when we had done cost minimization. Notice here we have utility maximization, there we were doing the cost minimization. It is good idea to pause and think that why in maximization and minimization you are getting exactly the same condition. The only change is that there we had MRTS, but mathematically they are the same. Here we have MRS. The argument that we have used, as I told you earlier, can be called arbitrage argument, and our end result comes out to be mu1 divided by p1 is equal to mu2 divided by p2. That is what we have. Now, it is also important to understand what is mu1 by p1 or what is mu2 by p2. So, let us say that earlier you had 100 rupees, for example, and you were buying x1 star unit of good one and x2 star unit of good 2. Now, let us say from somewhere you get 1 rupee extra. Again, this is approximate because 1 is a large number. We should make very small change to argue about it, but for logic it gives us good intuition, it helps us understand. So, if you get 1 more rupee and you do not, how should you spend that 1 rupee? So, in 1 rupee if you spend it on good one, you will get 1 by p1 unit of good one extra. And how much would be the gain on utility? The gain on utility is going to be mu1. So, this is the gain in utility if you spend it on good 1. If you spend it on good 2, this is going to be your gain good 2. Now, the thing is that at optimal point mu1 divided by p1 is equal to mu2 divided by p2. So, it does not matter in, if you were not optimizing, then one could have said that if mu1 divided by p1 is greater than mu2 divided by p2, spend your extra rupee on good one. Otherwise, you could have said, let us say if mu1 by p1 has is, if it is less than mu2 divided by p2, you could have spent on good 2, because that is what gives you more bang for buck. Okay. So, that is, but here at optimal level they both are equal. So, if you get very small additional income, then it does not matter whether you spend it on good 1 or good 2, because both are equal. So, you are indifferent. Why are you indifferent? Let us also understand the logic that if you have, this is your isoquant and this is your budget line. When we say, because this can also be written as mu1 divided by mu2 is equal to p1 by p2. What does it mean? That the budget line coincides with the MRS, the slope of that indifference curve. I should repeat, what is indifference curve? Combination of all the bundles that gives you the same level of utility. Graphically, they are very similar to isoquants, because in production x1 and x2 are inputs. So, we talk about different combination of x1 and x2 that gives you the same level of production. Here it gives you the same level of utility. So, the slope of indifference curve is MRS and slope of the budget line is this. They both have to be equal. So, your mental exchange rate, and what is your mental exchange rate? The exchange rate that your mind is willing to accept, so that you remain at the same indifference curve, you are not changing the curve. And your market exchange rate, how much is the market exchange rate for good? It is P1 by P2, they are equal. Let us say slightly differently that MRS is not equal to the market exchange rate. Let us say your mind is willing to accept 3 units of good 1 for 1 unit of good 2, and the market has the rate that says 2 units of good 1 for 1 unit of good 2. So, you have a different exchange rate. So, in your mind 1 unit, let me write here on top, 1 unit of good 1 is equivalent to 1/3 unit of good 2, and in market 1 unit of good 1 is equivalent to half unit of good 2. What should you do if you are optimizing? You should give up, hear me out, you should give up 1 unit of good 1 and you should get half unit of good 2. You would be happier. Why? Because your mind was willing to accept for 1 unit of good 1 just 1/3 unit of good 2, but instead of that you are getting more than 1/3, that is half you are getting, half is more than 1/3. So, that will make you happier. Of course, in my mind I am assuming that monotonicity is satisfied, it may not be satisfied, then condition is going to be different. But here if monotonicity is satisfied, this gives you higher utility, and you will keep on doing such exchanges till both exchange rate becomes equal. You cannot do such arbitraging and making you better off. So, that is what is the argument here. Now, we also saw that if your income goes up by 1 rupee, what happens to your utility? Your utility can go up by mu1 by p1, or your utility can go up by mu2 divided by p2, but at optimal level they are equal. So, it does not matter whether you spend it on this good or good 2, your utility is going to go up by the same amount. So, we can call them, this is marginal utility of income. Notice that inherent assumption is that this person is already optimizing. So, when we calculate marginal utility of income, we assume that the person is optimizing, but the person is buying the bundle that gives him the highest possible utility. And in that, again, when one more rupee comes, whether he spends on good 1 or he spends on good 2 or he spends x of 1 rupee on good 1 and remaining on good 2, does it would not matter as long as this 1 rupee increase is very small in comparison to I. It would not matter whether you spent it on good 1 or good 2. So, these two are equal and they give you marginal utility of income. Let us come back to a situation in which our optimal bundle happens to be x1 star comma 0. Remember the argument that we had given earlier, that we take little bit of money and spend it on good 1. That we can still do. We can take little bit of money and spend it on good 2 and we will get that delta I divided by P1 multiplied by mu1, and because now we are spending on good 2, this is going to be delta I divided by P2 mu2, and this has to be less than or equal to 0. The other part was that we took money from good 2 and spent it on good 1. In this particular case, how much money we are spending on good 2? P2 x2 star or P2 multiplied by 0 is 0. So, we cannot spend, if we move di from good 2 to good 1 in this situation, it means we will be spending negative amount of money on good 2, which is simply not possible. So, the equation or inequality that we had obtained from the second one, that this has to be less than or equal to 0, is no longer possible because we cannot do that. So, the only thing that we can ensure in this particular case, that mu1 divided by P1, we can bring it to the other side, has to be greater than or equal to mu2 divided by P2. So, one point I want you to pay attention to, that we did not say if this is the case, this will be the optimal solution. What we said, if this is the optimal solution, then this has to be the case. And similarly, for the sake of completeness, if 0 x2 star is the optimal solution, it means this is the case. So, let us understand it. What we are saying, again we will bring this 1 extra rupee, 1 rupee that you bring, if you spend it on good 1, mu1 divided by P1 you get as marginal utility of income. If you spend it on good 2, you will get this as a marginal utility of income. It so happens that this entity is greater than this entity. Okay? So, you will spend your income on good 1, and if you keep on spending your income on good 1, and of course, the assumption, typical assumption is, because we are talking about shape, as we move in this direction, you know, good 1 in terms of good 2 start becoming cheaper and cheaper. But it so happens that in some cases it does not decrease in this way, and even though if you have exhausted all your income and mu1 divided by P1 is still greater than mu2 divided by P2, what would you do? You will not buy any of good 2. Okay, just for illustration you should understand, and in that case what would be the solution? Your solution on the budget line, it is going to be here. All income would be spent on good 1 and no income will be spent on good 2. And I can give you an example. Remember the linear production function. Similarly, we can have linear utility function when goods are perfect substitute. The utility function is, let us say, is x1 plus x2. So, how would it look like? The indifference map is going to look like this, parallel lines. Let us say 1 unit of good 1 cost 2 rupees, so 2 x1, and 1 unit of good 2 cost 4 rupees, 4 x2 has to be less than, or we can say is equal to 100. What it means, that if you spend 1 rupee on good 1, you can get half a unit, and as utility function is x1 plus x2, mu1 is equal to mu2 is equal to 1. So, half a unit of good 1 will give you half a utility. Again, half a utility does not make any sense if we change the utility scale, but as we are comparing everything on the same scale, so it would remain the same. And if we spend 1 rupee on good 2, what is going to happen? You will buy 1 by 4 unit and utility will increase by 1 by 4. So, what is good idea? It is good idea that you spend your money on good 1, and as it is linear, the marginal utility is never changing, and as market price is not changing, we are taking it as given. So, what will happen? The answer will be that he spent all his income on good 1. So, budget line of course will have a slope, we can say from here the slope is 4x2 minus 100 minus 2x1, that is the budget line. I am just rewriting, or x2 is equal to 25 minus half x1. The slope here of utility indifference curve is minus 1. So, it is going to be flatter, and so this is going to be like this. Of course, it is not to the scale, let us say this is 100, this is 100, and this is this is 50 and this is 25. So, of course, the optimal point is going to be at this place, and this is we have as corner solution. So, requirement for corner solution is, of course, if the corner solution is on x1 axis, then mu1 divided by p1 has to be greater than by mu2 divided by p2, and if corner solution is on y axis or x2 axis, then mu2 divided by p2 has to be greater than or equal to mu1 divided by p1. So, that you should keep in mind. Now, let us consider a situation in which we have many goods. So, what we have here is that instead of talking in two-dimensional world, we have n different goods. How to proceed? Of course, the budget set will change like this. This is the way it would change, and if we keep it on the budget surface, hyper surface, because it is n dimensional surface. So, this has to be equal, not less than or equal to. We will come to the case when it happens it is less than or equal to. So, we have many goods. What we can do? We can, let us say, we can hypothesize that our original bundle which we think is optimizing is this bundle. We can pick any two, let us say ith item and jth item, and we will exchange between, we will keep everything fixed and we will exchange some money from I to j and j to I. Which condition we will get? We will get that MUI divided by PI has to be equal to MUJ PJ, and this has to be true for all I and j. Of course, the disclaimer is that all these are being consumed in the positive amount. So, when I say move money from xi to xj, it is possible because there is a positive amount of income being spent on I, and when we say move money from j to I, it is again possible as there is a positive amount of income being spent on j. So, if we do that, what do we get? mu1 divided by p1 is equal to mu2 divided by p2 and so on with mun divided by pn. This would be the condition if all goods are getting positive money income allocation for purchasing. This is the case. We can also say how to spend money. If we spend money on good I, we get MUI PI, and that is true for all I. So, if we are spending positive amount of income on, let us say 1, 2, 3, then mu1 divided by p1 has to be equal to mu2 divided by p2 and mu3 divided by p3. Why? Because if this is not the case, if this is greater, then we should spend little more on this and little less on this. So, the original proposal would not be the optimal proposal. And if we are not spending any money on all other, let us say from 4 to n, what it means that mu4 divided by p4 is less than or equal to mu1 divided by p1, mu2 divided by p2, mu3 divided by p3. That has to be the case. If this is not the case, it is greater, then you should be rather spending money on this fourth item and less on other items. So, this would be true for all on which you are not spending any income. This thing can be represented succinctly using something like this, that we are saying mu1 divided by p1, mu2 divided by p2, all let us say equal, because on all we are spending positive amount. So, we are writing it like this. What is this? This is marginal utility of income. We should be bit careful, but this is not just any utility, that is the maximized utility. So, we can write it like this: mu1 minus lambda p1 is equal to 0, mu2 minus lambda p2 is equal to 0, and so on, mun minus lambda pn is equal to 0. Now, there is a situation where this is not true. We have mui divided by pi, and in short I say lambda for I is equal to 1, 2, 3, 5, and is we say, because for all others j, it has to be less than this if j is not, or j does not belong to 1, 2, 3, 5. So, rather than writing it like this, we can say muj pj, that marginal utility of income, if it was spent on good j, has to be less than or equal to lambda for all j not belonging to 1, 2, 3, 5. So, we can say very simply that if positive amount of money is being spent on, if plus VE amount of money is spent on good I, and we say MUI, we rewrite it lambda Pj, or here also we should make it j, is less than or equal to 0 if no money is spent on good j. So, this is nice way to put it. Now, we have been talking about that maximize with respect to x, u x1 x2 such that Px is equal to I. But what if this constraint is not binding? What does it mean? That this is not the case, we have Px less than I, and that can take care. If we bring this and this together, we can get the case for this, and then that will solve our purpose. So, let us consider the problem in which we have this constraint. What it means? That the person who is optimizing is not spending all of his income on buying goods. So, because we have only two goods, what we mean is P1 x1 plus P2 x2 is less than I. What we can do, we can introduce a third fictitious good and we can say that P1 x1 plus P2 x2 plus x3 is equal to I. x3 is that fictitious group. It takes care of the slack, the difference between income and expenditure, and we say that the price of this slack is just 1, and this is fictitious, we are assuming, so this is fine. But what is the case if we have 3 good for optimization, because we are saying if x1 is positive, x2 is positive, and x3 because we are taking there is already slack, so it is positive. So mu1 divided by p1 should be equal to mu2 divided by p2 should be equal to mu3 divided by p3. It is also possible that x1 is also 0, for example, but both cannot be 0, because if both are 0 then no money is being spent and x1 and x2 are not real good, they do not give any happiness to this particular consumer. So we can accommodate that, but for time being let us say that both are positive. So this is the case. As u does not depend on 3, so mu3 is equal to 0. So this has to be equal to 0. What it means, because P1 and P2 are prices in the market, so in that case mu1 has to be 0, mu2 has to be 0. So when you are doing the optimization, you should go to the level where more does not give you any more higher utility, the marginal utility has become equal to 0. Okay. And that is the case, and we had this example. Of course, monotonicity is not satisfied. We had this example where this is a satiation point, bliss point, one can say, that gives you highest level of happiness, and so once you reach here you do not want to move out of there. So even if your budget set is like this, more you can move in this direction, but you do not have any incentive to move in that direction. So that takes care of non-binding constraints. This video was largely about mathematics, but it is important that we understand these mathematical formulation. You may be thinking that for last almost 1 week we have moved out of practical thing, doing little bit of theoretical things. It's also important to understand the theory. Pretty soon we will also going to learn thumb rule, which would help us. But to formulate the thumb rule, it's important that we understand the basic principle and mathematical way of doing things. So this is enough for this video. We will meet again in the next video. Thank you very much.